we're starting with kinematics because that describes how things move. And physics is about studying the motion of the world, of objects in the world. And so we're going to start by figuring out how to describe how things move and then move into why things move. So kinematics gives us a description, and we'll first start with talking about how we describe it. And we can describe it graphically, mathematically, and obviously with equations and data. So we're going to start with one dimension and 1D, and we'll use X as our direction. So you can sort of start with like a number line. Here's X, and say, let's say this is 0, this is maybe 5, and this is 10. This would be -5 and -10. And what we're going to look at is how do we describe how something moves from one point, say it starts at 5, so it starts here, this is the initial, and it goes to 10, that's the final. And so we can describe this motion in a number of different ways. We can say it goes from 5 to 10 in so much time. That tells us about speed and therefore what we call velocity. So we have velocity, which tells us how fast things go. It is a speed, how fast something's going, and a direction. So that means velocity is a vector, okay? So our velocity in this case, in a one-dimensional case, our vector velocity is going to be, at least our average velocity, is going to be our change in x, that's delta x over delta t, how far it goes over how much time, in the direction is going to be in the positive or negative I hat direction. So let's take this example. If this is our final, so delta x, that's just the change in x, that would be x final minus x initial. So if you start here and you end up here, and you do it and say, let's say that's a time of 2 seconds and let's say this is meters. Okay. So our average would be, of course, our delta x, which would be final minus initial, 10 minus 5, over the time, which was 2 seconds. And And this is meters. So this would be 5 over 2, or 2.5 meters per second. And then this would all be in the x direction, in the positive x direction. So this would be in the I hat direction. That's the way we signify in the positive x hat direction. Now we can go in the negative direction. We could start at the same place, redo this, and say we start here. This is our initial, and we go over here and make this our new final. So for this one, then we can say our delta x for the blue is going to be our final, -5, minus our initial, which was 5 meters, or a displacement of -10 meters. So this distance that we go, this is called our displacement. And it is a distance and a direction. So this would be -10 meters in, of course, the I hat direction. Okay, so displacement is also a vector. So this is a vector, and our velocity is also a vector, because it has a scalar part, a size, a speed, and a direction. And a displacement has a distance, how far we've gone, and then a direction. In this case, in the I hat direction, or if you prefer, you can think of the negative as associated with that I hat and say it's 10 meters distance in the negative I hat direction. Okay, so this average velocity here, our V average, is going to be our delta x over delta t, which would be a -10 meters in the I hat direction. And let's say that time was like 3 seconds. So over 3 seconds, and that gives us a -10 over 3 meters per second in the I hat direction, in the negative I hat direction. Notice a negative doesn't mean anything other than the direction. So this negative really is associated with the direction. It doesn't mean that something bad is happening. Okay, so this is then, if you prefer, you can do 10/3 meters per second in the negative I hat direction. That separates that out. Okay, so that's our average velocity. But how we do this, we might start slowly and speed up, or from this first one going from 5 to 10, it might be at a constant speed, running at a constant pace. But we don't know. We could be speeding up or slowing down. So if we want to move from an average to finding our speed at any point, then we go to what's called the instantaneous velocity. And for those of you who have already taken calculus, who aren't taking calculus right now, you will recognize this. Our velocity, and we won't have any subscripts, this will be our usual velocity that we look at, is really, as we take this delta t smaller and smaller, limit as delta t goes to 0 of delta x delta t, this becomes something you should recognize from calculus as a derivative. Now, you may not have seen a derivative of a vector, so we can also write it as just dx dt in the I hat direction, and that works fine. Okay, so this is a derivative. Okay, and so if you're not remembering that, then you may want to review that. If you haven't gotten there yet, that's okay. I'm not going to expect you yet to take a derivative, but you will be doing this fairly soon in your calculus class if you're taking it right now. Okay, I just threw that at you, so I want to now show you sort of where that comes from, and that shows up in a different representation for velocity. So I think it's helpful to see how we get from average to instantaneous velocity instead of just doing it mathematically. And I find that a graph, which is what I mean by another representation, can be helpful. And so if we take, for example, a plot of position versus time, then we can start at this position. Let's say we start at time equals 0 at x equals 5. We'll call this 5, and that's time equals 0, so that's the first point. This is x equals 10, and let's say this is 2 seconds later. Okay, and so we go from here to here. And we could do this in a number of different ways, but let's start with just one example. It could curve like this. And so we could go from 5 to 10 like this, and what this actually turns out to be is a situation where you're speeding up. And so if we look at this, the velocity versus time, the average velocity is taking this point and this point. This is what we calculated, and we're really finding the rise over run of this pink. So our average velocity, right, is delta x, that's this, over delta t. Delta x over delta t. So it's our slope, right? Slope is rise over run. That's our slope. So our velocity is a slope of position versus time. And that's a useful thing because we can look at these and we can say something about the slope as we go along. If we look, for example, at the slope at any one point, that is what we mean by our instantaneous velocity. So I want to know how fast this person who's walking from 10 to 5 is going at any one particular point. What's the speedometer reading? Then if I want to know at this point, say at, I don't know, this is 1 second, that's like 1.7 seconds in, then we find the slope, that's the tangent here, right? That's our slope, right? And so that slope right at this point, it looks maybe at time equals 1.8 or 1.7 seconds, then our velocity, which is our instantaneous velocity, is going to be the slope at that point. And that's really our derivative. So in calculus, what you find is you find your slope, your tangent to the curve, is finding your derivative, and you spend a good deal of time in calculus figuring out how to calculate this derivative. But all it's really doing, of course, is it's taking this rise over run and taking it for smaller and smaller time chunks. So that's why it becomes this limit as delta t goes to 0, to use the mathematical language. So our v at any point is our derivative dx dt. If you haven't gotten there yet, just think of it as a slope, because we'll be able to calculate it as a slope. Okay, and so that's our instantaneous velocity. Our velocity at any point is found from the slope. That would give us really our instantaneous speed, and then our direction. So this is v. The direction is either going to be plus or minus I hat direction, because we're just in one dimension. We're running along this number line, where to the right is positive and to the left is negative. That's our convention. So this would be our plus direction. Maybe I should have said that to start with. And then going this direction would be our minus I hat direction. Okay? So that gives us what's going on. And typically, you'll see a notation like this, v vector as our slope dx dt in the plus or minus in the I hat direction. So that's our speed, and this is our direction. And you'll see sometimes the notation v, which is equal to the magnitude of the velocity, and that would be our speed. And so in practical terms, our instantaneous speed, or our instantaneous velocity, so if you think about your speedometer, that's reading an instantaneous speed. The speed at any instant, it can go up or down, often goes down, right, when you see a police officer. Your average speed would be, how long does it take me to get to the Tampa airport from Eckerd? Well, if I measure that time and take the distance and divide it by that time, say it's like 20 miles or so, and I divide it by the time, that gives me my average speed. But if the police officer pulls you over and says, hey, you were going 80 miles an hour, arguing that, but my average speed was only 55 miles an hour, so I shouldn't get a ticket, is not going to go very well. What that just means is you were going 80 miles an hour when you were pulled over for a ticket, but you were stuck in traffic and going, a slower speed, 20 miles an hour for a little while, as there was a backup on the interstate going that way. So we have here average speed coming like this, average velocity, then the vector average velocity would be delta x, delta t with the vector. That includes the direction. That's what the vector has. It has a magnitude and a direction. And then the instantaneous, think of as like your speedometer measurement with a direction. So speedometer plus a compass that's telling you the direction that you're going, or a GPS that's telling you the direction that it's going.